you might find it very useful to put it all in one place together so it's all very organized mentally. So the first thing we want to talk about is what are the things that are critical in a simplified answer. And the first three things we're going to talk about are the fact that you can't have any negative exponents. You can only have one of each base when you're done, and that any mathematical operation that you can do has to be done. And here's what that could look like. So no negative exponents. If you see something like 1 over b to the negative third or b to the negative third remaining when you think you're done, you're not done yet. That was a very, very common thing we've been seeing is people not realizing that the negative exponents have to be resolved into positive exponents. If you see something like this, where I have a b on the top and on the bottom of my division bar, you need to simplify still. You should only write each variable once. And frankly, when you're talking about constants, if it's fully simplified, your constants should probably both be prime numbers, or at least numbers that do not share factors, right? Composed of no same numbers, right? So if you have an even number on the top and an even number on the bottom, you know you're not fully simplified, just like if it was a fraction, which it really is. And then if you see something like this here, where you notice I have a 2 in the top and a 6 in the bottom, well, I can do division there. I can turn that into a 1/3. And you see the c still has a 0 on it as an exponent. I can simplify that to a 1. So neither of those should be in a final operation, a final answer, because both of those should have been resolved. Okay, we've talked about implied values several times as well. I mentioned that when we talked about the exit ticket. And I just wanted to give you this in sort of a clear form if we haven't seen this before. So if I start with some variable, we're going to use a, I can say, obviously a is equal to a. That's pretty logical. But I can also say a is equal to 1a. And there's an implied coefficient. I can say that a is equal to 1a over 1, because there's my implied denominator. And you've used implied denominators for years. When you've been doing addition of fractions back in 4th grade, you started using implied denominators. And now we're also realizing that you can also say that a is equal to 1a to the first over 1, because we have an implied exponent there. So using all of these implied numbers that we don't bother to write explicitly most of the time can be very powerful. And that implied exponent is critical, because any variable that you see that doesn't have an exponent really has an exponent of 1. We just didn't bother to write. And a lot of people are forgetting, and because they don't see the exponent, and because you're not adding the exponent manually when you get the problem, you're forgetting to deal with it later on, and you're just pretending then effectively like that variable just went away because it didn't have an exponent. You can't do that, right? So I would definitely copy this down into your notes, that to remember that each of these things are going to trip you up when you're doing math in the future, because you can't just ignore like variables without exponents when you're dealing with exponents. It still has to be accounted for. So I'm going to give you guys a moment or two. If you want to screenshot that, that's fine. Obviously, you'll be able to go back and look at the recording and get it that way as well. If you're taking notes by hand, I'll wait for just another moment or two. Okay, so the next thing we're going to talk about, and this again is all in your notes. This is just an overview, but if something I'm saying kind of catches you odd, or you go, I don't quite understand that, please just send me a chat and I'll take it from another angle. So we've talked about multiplying by the base whenever you want to increase by a power, right? So if I want my exponent to increase by 1, I use multiplication to make that happen. And if you think about the rules of multiplication we've learned, this makes total sense. And if you think about that implied exponent, this makes sense, because this is a to some x to some exponent a times x to the first power, right? Because there's my implied exponent, which would result in x to the a plus 1. And this totally follows the multiplication of powers rules that we've been looking at. And it works very clearly here, right? Because that's how we went from x to the first to x to the second, is we multiplied by the base with the implied exponent of 1. 1 plus 1 equals 2. So even when we were very first starting off, so when would we need to do this? You don't necessarily need to do it, but it's important to see that increasing by one base is really the same thing as what you're doing in the multiplication rule, that this is all connected together. And this actually can be very powerful, because you may end up at some point. Remember when we very first started and we were building our powers out of pieces of bases and pieces of exponents, and we said that you could in fact have a variable up here where the a is, right? So I could give you something funky where it was, say I said that I wanted you to multiply x to the a plus 1 by x to the n plus 1. Well, you can do that if you have these kinds of rules. So it's not just about going up by 1, it's by going up by anything. And if you don't know what a is, then this is the only way you can write this. So you will see stuff like this later on in math. Okay, but this is the general pattern that we're describing when you see something like this. This is the general rule for that. And then on the other side, dividing is what you do to go down by a power, to decrease the exponent by 1. And so you have a rule that looks very much the same. If I divide by the base with its implied exponent of 1, then I could say it's x to the a minus 1. Right? So this is what we started off doing in our very first lesson on exponents. Because remember, we went through and looked at how do I get down into my negatives, and to go down to my negatives, we divided by the base. And this is the general rule that allows you to do that, is every time you divide by the base, you subtract 1 from the exponent you had already. Okay, so those maybe look a little new, but they're effectively the same thing that we've been talking about the whole time. So you don't need to bother to copy down everything on the bottom. If you wanted to copy down maybe this first box line there and the boxed equation up above, you could certainly do that. Okay, I'm going to go on to the next slide a minute. So we know the 0 power rule. Anything to the 0 power equals 1. Right? Hopefully that's not something you need to write into your notes at this point, but I wanted to just make sure it was captured in here, that doesn't matter what you put in here. That's why I use the word anything, which is not exactly a mathematical term, but it doesn't matter what you put in here, how complicated, how big, how ugly, how small, how silly, it's still going to equal 1. So reciprocals. We've learned that this is true, that if I have a -1 and a 1, you know that's going to have to produce a 0. And you know x to the 0 is 1. Okay, so I have a question. Why is anything to the 0 1? And it's because to go, if you recall, I don't have it in here right now, but if I have x to the -1, which is really 1 over x, and I have x to the +1, which is x, and I multiply them together. So 1 over x times x equals x over x, and anything divided by itself equals 1. So that's how we get to it being x to the 0. All right. And so we know that these are both true statements. And from there, and you can kind of get to and from any place here. If I were to divide both sides of this bottom, or the top really, either of these, by x to the -1, right? So I divide this side by x to the -1 and this side by x to the -1, I would end up with this, which we've seen before, that x to the -1 is equal to 1 over x to the -1. And you can also, if you divide both sides by this, get to here. And we've been playing with this for, a couple weeks now, that if I end up with a negative exponent, I take the reciprocal and I change the sign. And really, you can go from any piece of this to any other piece of this. And you could, as long as you kept these two numbers the same in magnitude, it would always be true. So if it was x to the negative 2 would equal 1 over x to the second. Right? So, and you could change the letters as long as the bases stay the same and the magnitudes of these, the absolute values of these two stay the same, it'll always be true. Okay, so this isn't new information. It's maybe presented in a slightly different way, but it's not new information. Does somebody have a question on any of this? Okay, so we had three main things that we learned after that, which were multiplying, treating a power as a base, and dividing. And we're going to go through each of those. And I'm going to ask you to work some problems on your paper. And then I'm going to show you some examples that you could copy down if you chose. So we know that our multiplying powers rule was that you add the exponents. And we wrote down something that looked like this in our notes when we did that. That if I have x to the a times x to the b, my end answer is going to be x to the a plus b. So I want you guys to write on your paper x to the second times x to the sixth and figure out what that would be. And you should be able to do it following this exact rule and come out with, you should have come out with x to the eighth, right? And if you did any combination of positives or negatives, you would actually come out with, in this case, different numbers each time. And here's that one I just had you work. X to the second, x to the sixth equals x to the eighth. And you don't need to worry about copying this down here unless you really want to. You could certainly screenshot it or come back and look at the video. But hopefully you see that there's a similarity between those two bottom lines. One is expanded notation, and then the other is our rule. But in both cases, you're really just adding one over and over and over again. So I would recommend you make sure you have this boxed part in your notes. And you could certainly pick one or more of these examples if you wanted to illustrate this rule. And hopefully you already wrote your x to the second times x to the sixth example in your notes as we were talking. Okay, a power as a base. In this case, you multiply exponents. So our rule was this: if I have x to some exponent a, and I apply the exponent b to this entire base, then it's equal to x to the a times b. Okay, I can go back. Just give me a second. I'm going to go back and then we'll come forward again. I had a request to go back to here. So whenever you're done getting what you need from there, let me know, okay? Okay, does anybody else need a little more time to copy something down on this if they wanted? All right, thank you for letting me know I was going too fast. Okay, so we were here before. And if it helps you, you might copy down this note to remind yourself that really when we multiply, we're just adding over and over and over again, which is why this rule actually works exactly the same as the one before. It's just that now we're adding this to itself over and over again this many times. Where before, if you think about it, the exponent that was in here was that implied exponent of 1, but really it worked the same way. Okay, so again, let's pick an example. If you had x to the second and you are raising that to the 6th power, So x to the second to the sixth power, what would you end up with as an answer? So put that one down in your notes, and we'll look at the answer in just a second. So x to the second to the sixth. So if you did it with some negatives in the mix, you would end up with one of these answers. Okay. And if you recall, we said that whether it was inside or outside, if you had a negative and a positive, you would end up with a negative answer. If you had two negatives, you would end up with, I'm sorry, if you had one of these, you would end up with negative. And if you had both negatives, you'd end up with a positive. And for the one that you should have just worked, you would have ended up with that same positive answer, because a positive times a positive equals a positive. And you could think about it one of these two ways. Right? You could say, well, x to the second times x to the second over and over and over again, 6 times. So 6 times 2 equals 12. Or you could add it up, and either way you come to the same place. Because repeated addition is the same as multiplication. Okay, I'm going to go on to the this is the last slide that we're going to take any notes on. And this is dividing powers. And our general rule for dividing powers was that you subtract the exponents, right? And if it helps, you could think about it that really when you divide, you're just multiplying by the inverse. So instead of multiplying by x, I'm multiplying by 1 over x, which is basically the same as dividing. Just like subtraction is just adding negatives. And so here, you can think, I'm going to subtract these two from each other and do a minus b. Or some of you like thinking of it better as I'm gonna multiply by the inverse. So kind of however it makes sense to you. But this is the way we often write the generalized rule. You've seen this before, a minus b. Actually, you might not have seen this rule, but this is what we have been doing. And so if you had x to the second divided by x to the sixth, you would be able to use this rule. So if this was 2 and this was 6, you would get x to the negative third. I'm sorry, x to the negative fourth. Apologize. Okay, so some examples. And just like with our multiplication, you end up with the same absolute value here, but with now it's opposite opposite signs. Okay. So here we have some of them are 1 over or just itself, and then these two link up again, right? 1 over x to the fourth or x to the fourth. And this is this part that we just covered last time. So if there's a part you're the most uncomfortable with, it's probably this piece here. Right? But these follow the rules we talked about. If I subtract the bottom from the top, -2 minus 6, I get a -8. Okay, does somebody have a question on division? We're going to go play a game now. So if you're feeling stuck when you get a problem, you should look at what we just wrote in our notes, because almost certainly with the tools that you just wrote down in your notes, you should be able to help work your way through the problems. So the question is, what side do you subtract from? Are you asking which of these sides you subtract from the other? Okay, so let me switch to a document camera, and I will show it to you a little more conventionally as a stacked problem. It's probably that I did not write it as stacked problems that's making it a little bit funny for you. So what you were seeing just now was, let me get back so I can see what you guys were seeing. Oops, sorry, it's gonna change size again. Okay, so our rule was, the way it's written on the slide was this way. x to the a divided by x to the b. But if I wrote it as a stacked problem, it would be x to the a over x to the b, because these mean the same things. And at this point, you could think of it a couple ways. You can say, well, this is x to the a minus b, right? Because I'm subtracting the bottom from the top. And another reason, part of the reason why this works this way is if I told you you could rewrite this, you could write it as x to the a times 1 over x to the b, right? Because these are the same. And we know that 1 over x to the b equals x to the negative b. Because we talked about that when we talked about reciprocals. Let me zoom in some. I feel like maybe my handwriting's not big enough. Let's try that instead. And if this is true, then I could rewrite this as x to the a times x to the negative b and turn it into a multiplication problem, which is the way some of you prefer to think about this. And I would still get to x to the a minus b. So whether you think about it as division, whether you want to turn it into multiplication and think about it that way, one is simply the opposite of the other in a way, and so you can do them both the same way, but you still come to x to the a minus b, whether you did it as a stacked problem as division or whether you turned it into a multiplication problem. Does that make sense? Okay. Is there something about any of this for division that isn't making sense to somebody? I know lots of people are using different approaches, and there are many valid approaches. But this is how we explain that generalized rule that we just put up, which was that x to the a divided by x to the b equals x to the a minus b. Okay, so that's what you would have written in your notes, but you could also have written it as a stack if you prefer to think of it. This is where you see most of your problems more conventionally. Okay, I'm not seeing any raised hands or any more questions in chat. So I'm going to switch us over to a game and we're going to practice this stuff. All right. Hold on. I'm just going to stop sharing this. I got to go